Hello, wonderful people of the internet, and of course, MIT Class 18S191 on computational thinking. Today, we're going to be continuing the discussion we had on Tuesday and also the Tuesday before that on ray tracing. If you guys weren't here for those lectures, essentially what we did is we did a two-dimensional example of ray tracing where we generated a spherical aberration image over here, and this was done last Tuesday. And then the past Tuesday, we implemented this fully in 3D, which is this image over here. Now, what we're doing today is more or less a live coding session of this image over here, discussing some of the details that we glossed over in the Tuesday lecture and also last Tuesday's lecture. So today, the plan is to first is to show the bits of the code that we already talked about, just to catch everyone up and explain where we are and why we're there. The next is to write little bits of code that we haven't talked about yet. And then finally, we want to talk about why certain elements of ray tracing are particularly slow and ways we can speed that up. Spoiler, last Tuesday, Alan talked about parallelism, and we will be using that to speed up the example here. Now, if you guys haven't been watching this class or you don't know how this works, there is a Discord link down in the description right now. Feel free to click that and ask any questions you want. And also, the lecturers, Dave and Alan, are also available here on call. And they'll probably be interrupting me with any questions that either you guys have or they have about the code that we're writing.
A quick check. Are we live on YouTube? Sorry to interrupt.
Yeah, you should be. Let me just go over here. Yeah, it's right there. So everyone should be able to see everything.
Sorry. Okay, thanks.
Yep. Okay. So I suppose let's start with the prerequisites here. So before going into today's lecture, we assume that we've already discussed little bits of reflection. That is the idea of a particle of light hitting maybe some sort of mirror and then reflecting off over here, like it is on this far side of the simulation over here. And then we also talked a little bit about refraction. Now, refraction is essentially what you see coming into the lens, where light will enter the lens and bend towards the normal. And then as it enters another medium like the air over here, it then bends again. And this again is that spherical aberration image, a semi-focusing event at the end of the lens that we created on Tuesday's lecture, and also will be generated in the homework. Now, for the homework, I will say we are still working on getting that homework out to you guys. I created a very basic version of the homework, and it's kind of just going through playtesting right now. So once we're sure that it's at the level that we expect it to be at, we'll then give it to you guys. So that's where we're at with that. Now, the extension of this two-dimensional example over here to 3D is actually not as complicated as you might think, because as long as you have reflection and refraction working, you can essentially create a bunch of balls that can reflect light or refract light, and you basically just track the rays in the same way you would before. The big differences here comes with the fact that now we have to deal with cameras, and we have to deal with these rays of light bumping into more objects than you would typically expect. So here we're just dealing with one lens. Here we're dealing with, looks to me in the simulation, like 7 or 8 lenses. So because of that, we have a larger number of objects that we're hitting, and this can do different things. So before going any further, let's make sure everyone is up to date. This image I've been using quite a lot just to explain what ray tracing is. The idea is we're trying to create a, fully realistic 3D visualization of the world around us, right? So how does the world around us work? Well, we see a bunch of objects, and the way we see these objects is basically by the light bouncing off of these objects and hitting our eyes. So here we would see light coming from this lamp up here, hitting the orange, and then after hitting the orange, or mandarin in this case, it then bounces back into our eyes. Now, for two-dimensional ray tracing, this is literally the image that we would show, just the light itself hitting the orange and hitting our eyes. But because ray tracing is typically used in 3D, the way this will work for that is by creating a two-dimensional screen in here, and basically saying that each one of these rays of light will first hit an object and then pierce through this two-dimensional image plane and transfer its color information to the pixel that it hits. So these will be individual pixels that each basically ray of light can run into and transfer the color information into. So this is kind of where we're starting today. We have some sort of idea of a camera, which in this case would be my eyeball back here, some sort of idea of an image plane, and the idea that light is going to be piercing through the image plane. Now, as mentioned on Tuesday's lecture, in principle, light is going to be extending out in all directions from this light source in here. So what we typically do is instead of starting from, let's say, the light source to my eye, we'll actually start from my eye over here to the light source, or two other objects. This means that we have a smaller group of rays to deal with. We only have to deal with the span of rays coming from the lens or my eyeball through the image plane, instead of an infinite number of rays that are coming from any given light source. Or maybe an infinite number of rays coming from some sort of three-dimensional or two-dimensional image that light happens to be coming off of. So this is all discussed on the Tuesday lecture. I'm just catching everyone up. And now let's talk about the first bit, which would be the camera and the skybox. So we mentioned this. Oop, that is still black. We mentioned this on Tuesday, Tuesday. Essentially, what we're going to do here is we're going to model this thing that's called a skybox. And we're going to assume that our camera is somewhere within this skybox, and it's pointing at objects maybe over here. And so what we're actually modeling here is light coming from the camera, hitting an object, and then moving over here to the skybox, or maybe it refracts through and hits the skybox over here. It doesn't really matter. The point is light goes to an object and hits the skybox and transfers the color information not only from the skybox, but also from the object that it hits. Okay, so this means that in particular, we need to talk about how to generate the set of rays that are going to be extending from this camera to the set of objects. And the way I'm going to do this is by drawing, again, this two-dimensional image plane that looks something like this. And then we're going to basically find the position of the center of each of these pixels and send all of those individual elements to our camera in here. So all of these guys will act as different rays that are being projected from our camera. So if we have an image resolution of 1920 by 1080, which is a typical resolution for high definition images, then we've got essentially that number of pixels. So something like almost 2 million pixels that we're shooting rays of light through. And this corresponds to 2 million different rays that are being generated from the camera, hitting objects and then bouncing all around the visualization. So we're going to start there. And let's go over here and open up some code and talk about what we talked about on Tuesday and where we're going to go today. So right now we have this concept of a camera, which again has basically a set of all the pixels, the size of the image plane itself in like real world coordinates, so like 10 by 10 or something like that. And then a focal length, which is how far back the camera is from the image plane. So that's this distance in here. So we'll say this focal length, I'm just going to call it L for this picture. We also have the concept of array, which has a vector direction. I called it a velocity vector because we used it for time stepping before, but it's essentially just the direction of light, the position of the ray of light at the tip, and then a color element associated with that. In addition, we have the concept of a surface, which has some amount of reflectivity, transmission, and color. The idea here is that each object can either transmit light, it can reflect light, or it can just return back some sort of color information without reflecting or transmitting light. Now, I mentioned in Tuesday's lecture that we have some constructors for this, and here's a constructor there. The main thing with this constructor is that every object can do some combination of reflection, transmission, or coloring of the ray of light. And so we want to make sure that the amount of reflection, the amount of transmission, and the amount of coloring all add up to 1, just to make sure that we have all of the light coming in being colored at some, all light is, like we're not creating more light when it hits this object. We have the same amount of light being transferred through or reflecting off. So we're going to say that the input reflectivity, transmission, and color alpha value, which is the amount of translucence in that color, should all be equal to 1, and then I'm just outputting an error message if it's not. Continuing through, we then have the abstract type object. Again, this was covered in the Tuesday lecture, and we have different objects: a sphere, which has a position and a radius, and in addition to this, we also have the idea of a lens, a reflecting sphere, and a colored sphere. A lens is basically a sphere that is purely transmittive. A reflecting sphere is a sphere that is purely reflecting, and a colored sphere is one that is basically just colored, and you read in the color here. Finally, I have the concept of a skybox, and again, light will end at the skybox. It will always hit an object and end there. I have little auxiliary functions for creating a sphere normal, refraction here, reflection here, and then finally an image, a way to convert whatever image we get, basically all the different rays of light, into some sort of image for viewing. Okay. Lastly, we have these intersection functions, which were discussed on the last Thursday's billiard model. It's kind of similar to that, where we're going to be using the quadratic equation in order to determine whether we're intersecting here with a sphere. And it's a union of sphere and skybox because we assume the skybox is also a sphere.
By the way, we have a YouTube question. All right, would you like to take it?
Yeah. What's the question?
From Arrow Raider. Does the focal length determine the field of view?
Yes, it does. That's actually a good point. So let me go ahead and draw that here. So if we have the image plane here, and we have the camera here, we'll call it. If the camera is close to the field or close to the image plane, we'll have rays of light that span maybe this wide. But if we're further away, here's our camera out here, and forgive my bad drawings, this means that actually those rays of light will be more parallel in here because you're further away. So it's like the rays of light have less of an angle, so they span less. Yeah, that's a good question. Thanks for that. Okay, so here are the intersection functions. Again, because we did talk about this a bit on last Thursday's lecture, I won't be covering this too much. The idea is that, sorry about that. The idea is if we have some sort of sphere, I'm just going to draw it up here. Sorry, I don't have much room on this. If we have a sphere up here and we have light coming at the sphere, it will essentially interact with the sphere and go through it. Let me try to draw it bigger. In fact, let me just erase this image I just drew over here. So the idea is if we have some sort of sphere here, and we have a ray of light entering the sphere, it can return either 2 instances where it interacts with the sphere, 1 instance where it interacts with the sphere, or no instances where it interacts with the sphere. And the way we do this is by basically turning the equation to check how far the light is moving forward, which is just going to be the light's position. We'll call it, I'm just going to call it P for position. We'll say for the next time step, so P1 is going to be equal to P naught plus some sort of velocity direction times time. I guess I'll say V, I'll put a little dot here for V times time. And so basically we can turn this equation into a quadratic equation through some math that we showed on Thursday and also will be shown in the homework. And then if we solve this quadratic equation, it can have either 0 roots, 1 root, or 2 roots. And depending on the number of roots, we know how many times it's interacting with the sphere. And so basically we just return the time it's interacting with the sphere that's closest to the ray's position when we shoot it, when we return the interaction event. Okay. And finally, I have this idea of a pixel color. Basically, the idea is that we're going to hit the skybox at some location, and depending on that location that we hit the skybox on, we're going to return some sort of color. So, for example, if it's between negative 1,000, let's say the extents are 1,000, or positive 1,000 in X, we're going to color it kind of with a smooth gradient along Y, or a smooth gradient along X. So that means it's going to be less red if it's all the way over at negative 1,000 and very red if it's at positive 1,000. We'll have a smooth gradient in blue as it goes along the Y value. So basically we have a smooth gradient along red in X, smooth gradient in blue in Y, and a smooth gradient in green in Z. Okay, at this point, I think we can go ahead and start creating our function here, which I accidentally left. Let me go ahead and remove it. And so now we're going to start with this initializeraise function. Now, you can really choose how you want to write this code. I tend to write code such that I tend to write code in more of like a C style fashion. This isn't necessarily the best way to write code. It's just how I tend to write it. So for this, I'm just going to go ahead and start by creating some...
What is a C style fashion, if you might be able to...
That's a very good question. What I mean is that I come from C++, so I tend to use a lot of like mutable types, and I tend to do a lot of things where like I think a lot about how the memory is aligned. So I tend to like pre-allocate arrays and stuff like that, and then deal with that like pre-allocated data instead of thinking about them as objects in some ways. That's what I would typically say is the difference in my mind.
Thank you.
But yeah, it really just depends on how you want to write code. So here I'm going to say that the resolution of our simulation is going to be equal to some sort of the size of the pixels of the camera's pixels that we're reading in, which I think is just this in here. And then we're also going to say that the dimensionality of our image is going to be equal to whatever the camera size is. So that is to say, we have some sort of size, which is like 1920 by 1080, and we have some sort of resolution, which again is going to be like 1920 by 1080. Now, I realize I'm already being kind of a bit willy-nilly here, but again, the idea here is that we have some sort of physical size that's associated with the camera, which I'm just going to call its dimension, and then we have some sort of resolution, which is going to be 1920 by 1080. Now, here's the thing. Because we're going to be looking for each individual pixel, and we want the center of each individual pixel, we need some concept of a pixel width, how wide the pixels are in physical space. So I'm going to say the pixel width is going to be equal to whatever the dimension is, again, in physical units, divided by the resolution. So here we'll say that each pixel is like maybe 0.01, for example, real physical units. And that's like how big the door is, or how big the viewing plane is for our camera to look through. After that, we're going to say that our set of rays is going to be some sort of array of type ray. And I'm going to, again, pre-allocate data. This is what I was saying when I was talking about C-style code. I like to work on an array that's already created. So I typically will create these weird, like, undefined arrays that I then fill in. So this will just be the size of basically the pixel plane, the number of rays that we're creating. So it should be resolution 1, resolution 2. And this is going to be a set of all the rays that we're going to be dealing with. Okay, so now we can just say for I equals 1 to resolution 1. And I'm going to end that in here. And now we can say for j equals 1 to resolution of 2. And now again, this is something that was mentioned last time at one of our live lectures, that we could probably put this all in one big for loop, and that's also fine. I just like it in two different for loops. I don't know why, it's just a personal preference. And we're going to say that the pixel location, and here's where we get a little bit tricky, is going to be equal to, we now need an x, a y, and a z value associated with our pixel location. So its x value is going to be the camera's position in the x direction, plus 0.5 times the dimension of 1, minus I, which is its element along x, times the dimension of 1 divided by the resolution of 1, plus, and I'm actually going to move this down to the next line just because we're running out of space, 0.5 times the pixel width in x. Okay, so what are we looking at here? The idea is that we have some sort of camera, and we're just going to assume that the image plane is all just going to be along z. That is to say that it's just sitting flat. It's sitting flat down here. And then our camera is just going to be facing up in some direction. We're not going to deal with rotation of the camera or anything like that. It's just kind of sitting flat, and then our camera is looking at it from here in some sort of z direction. So this is z, and then x and y would be these directions in here, x and y, or maybe vice versa, so x and y. Okay, and so what we're going to do is we're going to say that, okay, so we're going to start at the camera's position, and then we're going to go back a little bit, and basically say that, I think there should be some parentheses in here that I missed. Oh no, maybe this is okay. We're going to say we want to go, so let's say the image width is going to be, let's say 1010. So like the physical size of the image is like, again, a 10 by 10 image, and we have like 1920 by 1080 pixels. So we're going to move back 5, which is going to be back the dimension times 1. So if the dimension is 10, we're going to say we're going to range from -5 to +5. So the way we do that is by saying it's 0.5 times the dimension of 1. And then we're going to, we start at 5 and go to -5. So we go from 5, and then we subtract out I times the dimension over the resolution. So this will be basically incrementing back down. So we start at 5, and then in some sort of pixel width increment, we go from, like, let's say 5 to 4.5 to 4 to 3.5, something like that. And then I just add in 0.5 times the pixel width, just to make sure it's centered on the pixel. It's kind of confusing, so take some time to think about it. But also, I'm severely out of time now, and I'm realizing how I did not realize how how little time 25 minutes is for some reason. I've done 2 of these already, and I keep forgetting how much time this is. So we're going to do times dimension of 1 minus I times dimension of 2. So this is going to be the y dimension here, divided by resolution of 2. And similarly, I'm just going to put this down on the next line, 0.5 times pixel width of 2. And then what I'm going to do is do something similar for z. So in z, what we're going to do is we're just going to say it's, again, there is no real dimensionality in z. It's a 2-dimensional image plane. So here we're going to say it's going to be 0.5 times the pixel width. Actually, it should just be the camera position in z. 3 in z plus the camera dot focal length. All right. And this, I think, should work if we do it this way. And then finally, what I'm going to do is I'm going to create for every ray, I'm going to create L, which is its direction, which is going to be equal to the normalize of the pixel location minus the camera dot p. And then I'm going to go down here and just say that the rays of the resolution of 2 times, this is a bit weird as well, but I minus 1 plus j. And actually, I think this is because the rays are one big one-dimensional vector, but in principle, it's a 2-dimensional image plane, so I'm just doing the indexing myself. Is going to be equal to ray, and then I'm just going to initialize the ray here with L, pixel location, and then RGB of 0. So it's all just black to start. I think I need one more parentheses and that. Oh, no, not that.
So here you're basically mapping your matrix of rays to exactly where it falls on this plane that represents the camera.
Yep, that's exactly what I'm doing with this. It's a bit tricky, but yeah, I'm just trying to find a location of each individual pixel, and then after I find that location, I'm then sending a ray through. Now, in the interest of time, I've actually shown every other aspect of this code already in previous lectures. So what I might do is I might open up some other code and play around with that, because I think at this point we've shown basically all of the elements separately. And now if we show the code itself and we just show it running, we can actually do some interesting discussions here about parallelization and stuff like that. So let me just really quickly write this. Go ahead.
So sorry, if a ray hits an object and that object can reflect and refract, then you get 2 different rays?
Yes, that's actually where I wanted to go next. So let me open up a new file that, again, just forgive me for this one. Oh, I opened up the wrong editor. Okay, so here, if we go down to propagate, what I've done is I've dealt exactly with that here. I don't know why Vim syntax highlighting is coloring this red, but just pretend that's not happening. So what I'm doing here, the next thing I was going to write live, but there's no way I can get through with this live now, is the propagate function. The idea here is that it takes a ray and it looks at all the objects, right? And then it says, you know, we have a certain number of intersections that this ray is going to go through. It might only hit 1 object before stopping. It might hit 10 objects before stopping. The reason I want a number of intersections here is just I need to have some way to end this ray bouncing around, right? And so what I'm going to do is I'm going to start by saying, basically, as long as our ray is moving in some direction, that is to say our ray is not, our ray's direction is not just a set of zeros, I'm then going to basically seek through all potential objects it could interact with and see if it's going to interact with any of those objects. Again, this is not necessarily, there's probably a cleaner way to do this, but this is how I decided to implement it here. And I basically said, I'm going to be looking for some sort of intersected object, and I'm going to say, have some sort of intersection location. So I'm going to say that its intersected location is just as far out, there's nothing that's interacting with here, and I'm going to say there is nothing that's interacting with yet. And then I'm just going to go through all the objects in the objects that we could possibly go through and say that, hey, is there an intersection with that object? If there is, then I'm just going to say our intersection final and our intersected object is whatever object we're interacting with. So like a sphere or something like that, or the skybox on the outside. And if this is the closest object that we're interacting with, we keep that, and we basically move it down into this loop down here. In this loop, what we're doing is we're actually creating a new ray that is moved forward to the position of that new object. So it's going to be the same ray direction, and then it's going to be the ray position plus wherever it's interacting with the new object and the ray color. And then what I'm doing is I'm creating 3 separate rays: a reflected ray, a refracted ray, and a colored ray. And basically, if our surface has any type of transmission component, then we're going to create a separate ray at that point called the refracted ray that basically just goes through and propagates forward after refracting. And then I do the same for a reflected ray over here. So again, it can reflect off, and then we propagate it through. And then we have colored ray, except in this case, we don't propagate out, we just color that ray, and we return that ray value. And then what I do in the end is I basically collect all of the different colors. So each ray will just go in its opposite direction and return some sort of color information. And that's how we have ray color in here. After that, we then say that our ray is not moving anymore. So we're just going to say that our ray is going to be, has stopped. It has returned color information, and it stops at whatever, whether the skybox or whatever object is returning the color information, and has some sort of ray color associated there. So the idea is we're just recursively calling this propagate function again and again. Yeah, and if it hits the skybox, then it just returns the color. Okay, so now the only other bit that I haven't spoken about with this file, I've already spoken about initializeraise just recently, is, well, I guess the raytrace function. Here the idea is we initialize the rays, we propagate all the rays, and then we just convert all the rays at the end to image. And now I've created this main function. Again, this is where my C-style coding comes in, where I like to have a main function that kind of calls everything, where I have a skybox and basically a set of spheres in here. So what I'm going to do is I have a separate Julia REPL up over here, and I'm just going to run, just so you guys can see that I'm running exactly what you guys see over here. I'm just going to run include 3dslim.jl, which is what I called the code. And in here, I'm creating a bunch of different spheres. I'm creating a lens, a reflecting sphere, a colored sphere, and then just other spheres that are somewhere in between. So this one has some level of some level of transmission and some level of color. This one has some level of reflectivity and some level of color, and this one has some level of all 3. It looks like. Oh no, just reflectivity and transmission. I created a blank image, which was 1920 by 1080, but just in the purpose of time, I'm gonna make it slightly smaller. And then I just run it after this by returning the ray trace here. So if I go here and I just run, I think I just run main, it will return back an image that I called check.png because I wasn't very good at naming. When this is run, I then want to do one more thing. So let me go ahead and open up a new Julia REPL. And this time I'm going to run Julia -t auto, which will basically allow me to run Julia in a threaded mode, and will allow me to use basically all the cores that I have at my disposal. So if I then run, again, include 3dslim, and we let this run over here, it is taking a bit longer than I thought it would, though. Maybe it's because I'm running so many, maybe it's because I'm also running a streaming at the same time. Let me check my cores. Oh yeah, my streaming software is actually taking a significant amount of my compute time, which is why it's taking a bit longer. So what I'm going to do is I'm actually going to make this image even smaller. And then hopefully this should allow us to run it in a reasonable amount of time. Cool. So, are there any questions that you guys want to ask, by the way? No method mentioning array RGB of n and undefined initializer. Okay. 330. This worked just a second ago, didn't it?
There was a question in Discord from Akshu that says, why are there 2 similar inner constructors for surface?
Oh, okay, that's a good question. So let's go up here and let's go to that code. Well, this one. So let's go to surface. Oh. So the reason is simply the first inner constructor is going to be Just the inner constructor, just to make sure that your reflectivity, your transmission, your color are all less than 1. The other one over here is just a way for me to easily call the surface function. So if, for example, I just wanted to call this as surface of like 1, 0, 0, 0 or something like that, it just allows me to more easily call it as a float 64 instead of calling it as a pure color. It just makes the function call a bit nicer. That was the reason.
Maybe you can just say something about why you used inner constructors instead of outer constructors that we've been emphasizing until now. So outer constructors are ones that live outside the definition of the struct, and inner constructors are actually placed inside the struct definition between struct and end. Why would you use those instead?
That's a very good question, because I did not realize we were focusing on outer constructors until now. Sorry about that. I didn't realize that was...
That's okay. No, it's good. It's good. I mean, but there's a reason why you used inner constructors, right?
Honestly, you can also use an outer constructor just fine. I'm not entirely convinced why this is not running, but it was just a second ago.
So I would say that you would use an inner constructor when you need to impose a condition to prevent you being able to construct the object. You know, for example, if you need some positive number inside your constructor, you can actually impose that and make it impossible to construct a version of the object with a negative number by using an inner constructor.
Right. Yeah, that's a good point. So these are both working with a... Yeah, Alan might have another opinion there. Sorry, I'm going to go ahead and cancel these guys, and let me see if I can figure out why it's not working when I just divide by 2.
It's very common in Julia, actually, to write to there's another response question on Discord. It's very, very common in Julia to write several different constructors, which just give you, as James said, different sort of convenience ways of creating objects. So, for example, you might have some default values that you want to have, and so you would actually end up writing several different versions of a constructor function.
Yeah,
it's a very common thing to do. So you might have one with where you pass in 0 arguments and it just assigns the values of all the fields automatically.
I got a segmentation fault. I don't know how that happened.
That should not happen at all.
So let's just do this then. End threads here. Oh, sorry. It's T auto. I don't know what I was thinking. It's been a long time since I got a segmentation fault in Julia.
Yeah, it's pretty rare these days.
Okay, it's okay. So we'll include this, and then we'll run main, make sure it works. What I was hoping to do was show you guys a bit about parallelization, and I guess I can talk about it here while we're just waiting on it to run. The idea here is that the propagate function basically takes an array, right? Let me just go to propagate here. So it takes in just array as a function argument. But let's say I want to modify this so it takes in actually a series of arrays, an array of arrays. In this case, it's actually pretty easy to parallelize with the floop demonstration that was provided by Alan not too long ago. The idea is you just do @floop, and I usually run threaded executable for j is equal to 1 to the length of arrays. And by doing this, you'll get a quick speed up. So if I just do @time of main here, I don't understand. It works with 1920 by 1080, but it doesn't work with 1920 divided by 2, 1080 divided by 2. So what's another good 16? Let's just
do 800 or something.
800 by 600?
Yeah.
Does anyone know why it would not work with a divided by 2? Is there some sort of integer logic going on there?
That is because that's making a
I was making a float.
Yeah.
Don't you need the divide symbol rather than...
Yes, that is precisely what I needed. Thank you for that. But anyway, so we timed this to be 12 seconds, 12.94 seconds. And now what I want to do is I want to run it one more time while we're finishing here without the T auto. So this means non-parallelized. And we're just going to include this and then run main, and we'll show that this is a quick way to parallelize it. Now, one interesting thing here is we're not actually going to be getting like a factor of 16 times improvement. even though technically I have 16 threads that can run here, we'll probably get close to a factor of 2 improvement. And that's because there's the generation of the rays is also something we didn't parallelize, right? And so since we didn't parallelize that, also because it's the first run of main, it might not be exactly the right time. But because we didn't parallelize the generation of the rays, and also because of this recursive element of the rays of light hitting an object and then splitting off into 3 others, we don't end up getting a factor of 16 improvement. We end up getting like a factor of 2 improvement or something like that. So that was the last thing I wanted to show.
Seems like that would be actually difficult to parallelize.
It is actually a little bit harder to parallelize than you might think. So standard ray tracing is considered pretty parallelizable, but because of that recursive nature, you'll end up seeing that some of your threads are just not acting while other ones are doing a lot of work. So again, we timed this to be...
is there a way you can rewrite that in a non-recursive way?
Yeah, so I think there might be, but that goes beyond what we had shown. Oh, it's a more complicated way to do it.
I mean, couldn't you just use some kind of stack?
Yeah, I mean, I guess you could. I'm not sure how Julia does it underneath, so...
I mean, effectively, that's what you do when you do a recursive call, I guess, but...
Right, that's what I was thinking as well.
You just do it explicitly with a stack that you keep pushing and you raise onto.
Yeah. So give me just another 20 seconds here. I'm so sorry I'm over time. I promise we'll be done after I run this time. But yeah, at this point, I think we've covered everything that we need to cover for ray tracing for you guys to be able to do, I think, cool 3D ray tracing demos and stuff like that. So let me time it one more time. So with...
I think you could take another 5 minutes if you need it, James. I think it's okay.
Yeah, okay. But honestly, this is where I wanted to stop, just timing the main function a bit. So this one took 9.497 seconds, whereas the one that we did for the non-parallelized version took about 15 to 16 seconds. So again, it's not a factor of 2 improvement. It's closer to a factor. It's not a factor of 16 improvement. It's closer to a factor of 2 improvement, and that's because of the same things that I said before, where you have this weird recursive thing where rays of light are hitting some objects and then bouncing off and creating multiple rays, and also because some of this code is not parallelized as it should be. If we look at the final image, though, we'll see probably a somewhat distorted image. So here's our 16 or 800 by 600 image. It's kind of squished a little bit because of the pixel resolution. But again, we do see reflection in this ball over here, both reflection and refraction in this ball over here, and a bunch of different things happening. So for example, light would come in and it would hit this ball over here, and then it sends off like 2 or 3 different rays, doing both reflection and refraction. And so that ball is probably the hardest one to compute because it has a whole bunch of things going on. But this one back here is relatively easy because it's just reflection, and the other ones aren't so bad. But for example, a ray of light would go in here and it refracts out to this one over here, or maybe it's this one back here, and then it reflects off onto this one, and then it reflects and refracts off. And so because of this, some threads just have a lot of work to do, whereas other threads don't. The point of this is that, first of all, there's a lot of tricky things with ray tracing that are kind of hard to figure out. Like, for example, the generation of the rays and moving the camera around and all that kind of stuff. And on top of that, you really need to think about how exactly you're going to parallelize this. So when we do this with GPU shaders or however you want to do ray tracing, there's a lot of these extra considerations that you need to do to make it actually work appropriately in parallel. I think that's actually a pretty good place to stop for today. And yeah, if there's any last questions, we can take those. Otherwise, we'll head off and chat with the MIT students in particular. Okay, so I think that's it. Thank you guys so much for watching. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And yeah, we will see you around next week when we have a guest lecture on Tuesday, and we'll see what we're doing on Thursday. It should be pretty fun. So I will see you guys then. Bye, guys.